Welcome to Data Brew by Databricks with Denny and Brooke. The series allows us to explore various topics in the data and AI community. Whether we're talking about data engineering or data science, we'll interview subject matter experts to dive deeper into these topics. And this season, we're focusing on large language models, or LLMs, while we're enjoying our morning brew. My name is Denny Lee. I'm a developer advocate here at Databricks and one half of Data Brew.
And hello, everyone. My name is Brooke Wenig, Director of the Machine Learning Practice at Databricks and the other half of Data Brew. And today I am delighted to introduce Omar Khattab, PhD student in computer science at Stanford University, and also the creator of the Demonstrate Search Predict framework. Welcome, Omar.
Thanks. Glad to be here.
So to kick it off, would love to just learn a bit more about your background. How did you get into the field of NLP?
So I did my undergrad in Carnegie Mellon's campus in Qatar. It's a very small kind of campus they have there. And it just has 4 or 5 programs in total. So I studied computer science, and there's no grad school. So doing research there as an undergrad is a unique and interesting experience. So I started working with one of the faculty there, Mohammed Hamoud, and we basically looked at large-scale analytics and parallel processing in various kind of AI or AI-adjacent applications. And one of our sort of last long-running collaborations before I graduated was we were looking at how to make information retrieval or search, more scalable and faster, and also just easier to program in for traditional models that work with term-based indexes, essentially what you'd see in Elasticsearch or traditional systems like that. So I graduated and I joined Stanford for my PhD, and I was talking to Matei, who is my advisor, and we had a few different things that we were thinking about, but they were all related to retrieval. So we one option was we could look into this weird BERT thing and the kind of what it could do in IR. It was the first uses of BERT had been in IR for just a few months at that point. BERT itself was a year old or a bit less. And there were interesting questions there about maybe doing indexing, like traditional indexing, but with BERT. And what would that even entail? We also had the other idea that was, obviously much more exciting in retrospect. I'm kidding, which was, building faster phrase search. So what if you want to search, in traditional systems, but match phrases in an efficient way? And, Matei suggested that the BERT thing sounds like it's going to be more relevant in the long run, and that that was obviously the case. So we started building this retrieval model that ended up being a lot bigger than we thought, which is called Colbert. And that's its own story. But through Colbert, I ended up sort of interacting with Chris Potts, my other advisor, who is an NLPer. And he encouraged us to start thinking of what this sort of retrieval stuff could do in NLP, and I guess through that, at some point, I officially, became an NLPer, in some sense.
Well, you have the honor of being the first person that I have met that identifies as an NLPer.
Oh, that I did not make that term up, but I probably heard it for the first time from Chris.
Fair. So I have to ask you, just because I've got a very sad state of humor. So I take it Colbert is not referencing to Steve Colbert or the Colbert Show, right?
Colbert is all about a technique, and I'm happy to talk about it for a bit. In fact, it's
as much as I'm joking, I do think it'd be actually helpful for the audience to listen to at least a little bit of the context of what Colbert is before we dive in deeper. Yes.
Absolutely. So before the technical side, Colbert is about a technique called late interaction, and we thought, well, late interaction, BERT, late show, gotta call it Colbert. So it stands for contextualized late interaction over BERT. We definitely worked backwards from Colbert, but the name does work out. So Colbert comes into in that space where in IR with BERT there were very unfavorable trade-offs. Either you work with what is called dense encoders or bi-encoders, we like to call them single vector methods because that's a more precise terminology, I think. And what these methods do is that they would take your favorite large by BERT standards language model, and they would run it on every document in your collection. So you're doing search, you have thousands, millions, hundreds of millions of documents, and you want to be able to retrieve relevant things from them given a query. So these methods, that's sort of the mainstream approach, is that you would take BERT and teach it to take each of these documents that you have and spit out this vector, maybe a dense vector, that has 1,000 dimensions or 700 dimensions, that is meant to represent the semantics in that context. And there's tons of research that looks at that. And then you have a query that you want to find relevant documents for. And what you do is you ask that same encoder to give you a vector, and then you do similarity search. Like, just give me, for this query, what are the nearest 100 documents, and I'm going to return them to the system or to the user, whatever the pipeline looks like. So that's one extreme, and that's sort of like the bread and butter of a lot of IR. On the other extreme, there are these things that are called cross encoders or re-rankers. And what these do is they say, hey, BERT is all about attention. So what we got to do to make it work as well as possible is allow it to attend to things, and to attend to a query and a document at once. It means that we're going to give BERT the two together jointly. We've got to condition the two together. What that means is now BERT can look at like all of the interactions between the terms, not just within the document, but within the document, knowing what the query is, and that makes it a whole lot more powerful. But the problem is it's not scalable, because now every time you get a new query, all of your representations of the documents are useless, because now you got to recondition again on the new query that you have. And we didn't like that trade-off. So what we started thinking of is, hey, is there a way to sort of bring balance into this? And what we realized was, maybe we can keep that independent encoding of the query and the document without resorting to cramming the representation into a single vector, and instead keep the token level decomposition that BERT has, but also that is known in IR traditionally to be something that's really powerful. Keep that decomposition, and basically for every document, we're going to produce a set of vectors, a matrix essentially, not a single vector. And the questions that this sort of raises is, well, now if your query is a matrix and your document is a matrix, how do you scale up similarity search? And Colbert, that's where Colbert gets really interesting, because even though we're changing into this like much more expressive scoring mechanism, it's created in such a careful way that it actually is very easy to scale up, and it's very easy to make this amenable to optimization. So you end up with something that is similar in latency, similar in space footprint, after a sequence of papers that we've published at Stanford here optimizing this, but a whole lot more robust and resilient to difficult search queries, and to transfer to new domains in search. So that is sort of like the I don't know how many minutes this has been, but maybe the 10-minute version of what Colbert is all about.
Yeah, that's awesome. That totally makes sense. That would be way more expressive and powerful, representing it as a matrix of vectors as opposed to a singular vector.
Yeah, actually, let me add like the key intuition there, because I forgot, is especially as to why it generalizes better. We basically hypothesize, and we see time and time again, that it's just inherently an easier task to encode a term given its context, given its context, than to figure out one representation that covers all possible questions you could ask about a document. So you're just capturing one term, saying like, hey, this person, they're saying bank here, and they mean actually the river bank in the context of somebody who's taking a walk. That's a much simpler concept than, oh, here's a document that's describing a story in which a person named this is taking a walk next to a river bank, and so that's a much harder representation to capture with a single vector representation.
And so how did all of this lead way into developing the Demonstrate Search Predict framework?
Great. So we built Colbert, Matei and I, and we saw lots of excitement around it. Chris had joined us, and he really sort of believed in this and thought, there's something very deep and serious here that we should explore more. And so Chris urged us to basically start looking into, NLP applications with the hypothesis that bringing retrieval into them will help NLP. And this has been basically the common theme of all of the stuff that Matei, Chris, and I have been doing over the past few years. So we built a system called Colbert QA, where we can answer questions over, like, say, a Wikipedia corpus using a Colbert retriever and some downstream language models. But the question is how to get them to adapt to one another and work together in a new domain. And we were actually quite surprised because if you just took Colbert and you applied it to that task out of the box before even any adaptation, it was already outperforming some of the state-of-the-art stuff at that time in that domain. And so that encouraged us to sort of just look into actually adapting it more and seeing what we can do in terms of quality there. We started looking at harder tasks later, where simply taking a user's input, which might be a question, and like asking Colbert to find stuff might not be enough. So say you might be trying to do fact checking over claims that are like a couple of sentences long. And these might not necessarily be something that's like there's a single paragraph in Wikipedia that tells you that is reasonable or not. It might actually be split across many pages. And so we looked into multi-hop search is what it's called, and we built this system called Baleen that uses Colbert-style retrievers, but in an iterative formulation where the retriever looks for stuff, finds some documents, asks the language model to read them, summarize what it's found that's relevant, and then go back to the retriever and then find more things, in the sense that sometimes finding some sources tells you what other dependencies or what more things you need to look for, essentially as a bridge to the final big picture or set of different small puzzle pieces that you're gathering in to inform your end task. And we ended up sort of collaborating with a number of great researchers here at Stanford and elsewhere at building a number of these systems. So like Ashwin, who was a PhD student here, he graduated. We built Hindsight. He led the Hindsight project. We built Colbert V2, looking more at like zero-shot retrieval, and a number of other systems. And around a year ago, a little bit more than a year ago, so in early 2022, we started thinking, well, great. So we've learned that retrieval is really key to doing a lot of really powerful things in NLP, especially in like these knowledge-intensive tasks where you want the model to be grounded in documents, to search for things and to find them and to cite their sources. And this can be I'll go on a tangent here, but this is really desirable because, well, maybe the model is making mistakes, as we all know, like they make stuff up or otherwise mistake things. It would be great if we could reduce the frequency with which that happens, but also perhaps more importantly, it would be great if when they do make mistakes or they don't, we can just check what was going on and see what they read and how they understood it and what they did based on it, so that when they're right or when they're wrong, we know what to trust. Like, hey, I told you something and I'm citing a source you do trust, but that source is not saying the same thing that I'm saying. So maybe I made it up. Or maybe I'm copying something reasonably from a source, but you actually don't think that source is particularly reliable in this topic. So you could just say, hey, like, okay, I know what was going on, and I'm going to choose not to. I'm going to do my own research, or I'm going to ask again until I'll let you know I don't like this source, and maybe you should try a different thing. So this is sort of established for us that retrieval and NLP should really exist together. But we didn't like the fact that each of the systems I mentioned, like Baleen and Hindsight and others, were a multi-month sort of very high effort, one or more PhD students working on a new architecture that is hard to develop for that one task. And we ended up with this architecture that is specific to that task. Moreover, it needed a whole lot of data because you got to train all of the components, the retriever to work with the downstream language model, and that was difficult. And what was sort of what we just shown at that point with Colbert V2 is that retrieval had reached a point where you could say just take standard Colbert V2 models or state-of-the-art retrieval models and actually just tackle tasks zero shot. Just give it a query in any domain that's reasonably vaguely related to its training data. It doesn't have to be aligned with it, and it will impress you. It will work pretty well. And obviously language models, well, at that point, few shot learning was all the rage, and GPT-3 was, increasingly central. Obviously, a lot less than it is now, but it was clearly something that a trend that was coming. And so you have these components that work really well at like relatively small, well-defined subtasks, and we've been building highly kind of, let's say, bespoke architectures by fine-tuning them. But the question is, what can you do if you took them off the shelf and try to like compose them in interesting, complex architectures? And what does that even mean? And what design choices exist? And how well could you do? And should you just like how should you glue them together? What primitives essentially emerge, what patterns emerge as you try to do that. And so we basically wanted to build a programming model, a framework, but more, eventually actually a fully fledged programming model that can express these sort of retrieval language model systems, in a few lines of code, and abstract away that recurring complexity that we've seen in building the other systems.
Well, this is really interesting. So you've covered actually a whole bunch of stuff. And so I want to actually go backwards a little bit. So for starters, when you're talking about DSP, you also had noted in the past that this idea of knowing what the sources are, like in terms of like trusting which set of sources, right? I'm curious within that context, like before we even talk about the programming language to simplify its retrieval, what's the context or by which you can go ahead and cite the sources? Like, do you also clarify that in your model itself that this is what people are deeming, or is this like customized per the individuals that's actually asking the questions?
So this is customized on a per task basis, and then on a given question. So you ask the system a question, it will by design not just be a black box that like has a lot of parameters that thinks really hard and gives you an answer. It is going to say, okay, well, that's a question. I'm going to generate a search query, and then I'm going to go to my favorite retriever and send that search query over a specific index of specific documents, maybe ones that you selected, maybe just the web, maybe Wikipedia, whatever, maybe Databricks documentation. And I'm going to find some sources, and then I'm going to take these sources, arrange them in some way, and then give them to some model that will use them to extract an answer or to generate an answer, or otherwise, just respond to the user, or any other number of like back and forth between these two components. And so now you could always open up that box because it's very transparent behavior, step by step, and see what happened. And from an HCI standpoint, you have all what you need, or at least you have a lot of different things that you could start exposing to users on a per application basis as to what you think you deem to be reasonable. To be clear, none of this means that the language model will necessarily say the right thing or even use the sources correctly. But as we continue to make that more and more, closer to being the case and more reliable, you have that visibility and you can see what happened.
Right. So, okay. And so related to that is the context within the idea that you're trying to reduce hallucinations basically of the model. Okay. Or having the model basically make up stuff or just outright say the wrong things. But then is there an implication that you would need to like provide the input of the said users, like this entire feedback loop of multiple users to sort of publicly showcase that as well, in addition to the original model or the visual process, so that way people can understand like how this model or this iteration of that model is making its choices? I'm just curious, like what would be the right context for something like this?
Yeah, so you wouldn't generally default to exposing too much, but what you can say is, for this, you are a particular user of a particular system that wants to be transparent about some specific subset of the workflow that it's doing. That we decided is the right things to be, we don't want to overload people, so because they're not going to do anything if we just give them like, a million words and then they have to like.
No, that's fair. Like it'd be the equivalent of me saying like, go look at the Spark logs. Now let me turn on verbose. Good luck, right?
Exactly. Yeah, so we're not going to be in verbose mode.
I'm trying to avoid that scenario, which is basically the cause of the question. I personally have suffered the context of seeing verbose Spark logs. I don't want to do that to anybody else either. So I'm just curious from the standpoint of like, then in the case of like these models, right? Like how do we find that right balance of the verbosity, yet at the same time you definitely need to know some of this information?
So let's actually pick a specific pipeline. Let's say you want to ask to ask questions about documentation of your favorite library. And maybe this library is not in the training data of the language model. Maybe the language model will not know the answer to many of these questions, both of which are very common assumptions that are very true. So what you could have is a pipeline that takes your technical question and then spits out some search queries, maybe several, and then searches with all of them, and then reads 100 documents in total. But then it selects one document or three. A few documents, and then it gives those to a language model again and says, hey, answer the original question given these documents. What you could show to the user is to find that answer that the model generated, and then maybe a heat map or some other thing over the 3 documents that were fed there. The user could look at this and say, well, these documents are not even related to what you're talking about. Or they could say, oh, that looks very reasonable and such. So they don't need the burden of like, oh, I generated like all these queries and I did all that stuff. They ultimately just need like a contract that says, hey, I found the following things and I did my best to generate this output based on it. You can check if these things are relevant and reliable, and you can check if I did a good job at summarizing them for you. And if I didn't, well, at least you know.
And so what's the best way that you've seen people incorporate that feedback back into the model itself? Of like a model has its answer for the question at hand and the documents that it used as supporting sources. What's the best way to evaluate this? I know you had mentioned that you can manually review it. Do you see a lot of reinforcement learning where people do a thumbs up, thumbs down? Is there any metric or objective function people can optimize?
So a lot of DSP, and we could definitely use this as an entry point to a lot of like how it works and what we emphasize there. Is a lot of DSP is about working in domains where the requirements might be constantly changing, or we don't actually understand the tasks very well, or they're essentially few shot, and you only have a small number of examples because you're writing them as you go. And evaluation is a very big question in this space. But we emphasize the fact that you're working in a highly controllable multi-stage world in a multi-stage pipeline, and you can much more easily evaluate the individual components and how they glue together than this big end-to-end black box system. So you could say like, hey, let me measure the accuracy of retrieval, and we have a good idea of how to like evaluate retrievers, or let me measure the grounding between the retrieval and the generator, or any other number of like subcomponents there. So I do not claim at all that we've solved evaluation, but we certainly help you break things down to a more manageable level. As to how essentially feedback goes, as you said, so feedback is not exactly the right concept for us. Of course, it's a very big topic, but we focus more on what we call demonstrations, where maybe I should like do a little bit more of a an overview of sort of the the way DSP does the things that we discussed. So let's see. Let's see what would you do if you did not have a programming model like DSP. So maybe that's a good place to start this. You would say, well, I'll pick my favorite retrieval model, and I'll pick my favorite language model, and I'll glue them together. So I'll give the input to the retrieval model, it'll find a bunch of sources, and then I'll concatenate them and give them to a language model and ask it to do a good job. And invariably, you'll find that it does not always do a good job. So now you're kind of, or maybe some other more complex chain. But now you're sort of stuck because prompt engineering, as it is called, does not really offer a reliable sort of systematic way to continually improve on these systems. So then you come to things like feedback, as you said. So maybe you're essentially at the mercy of your language model provider to do a better job next time in aligning the model with simple instructions. So then your same instructions, or the slightly better ones that you will write, will lead the model to do a better job at the task. Not alternatively, you could keep tweaking the prompts and have multiple of them if you want, and do like a little bit of a chain of thought or reflection or all the cool things that people are releasing, and they can be very effective sometimes. But it's a little bit unsystematic, and improvements may not necessarily add up, lacking a systematic programming model. So what DSP says is, well, let's think of what we do with deep neural networks. Well, what we do there is we don't just like come up with crazy architectures and implement them in matrix multiplications or in like NumPy or something, we go to something like PyTorch, a highly developed sort of abstraction or programming model that says, hey, you have layers, and they could be convolution layers or linear layers or recurrent layers or whatever it is. And those layers, they're just like a, individually, they're a black box that you define with a small number of like input and output behaviors or like parameters. And you tell me how to initialize it, or I'll just figure it out for you. And you can string them together, and that gives you the forward pass. And then you have maybe a little bit of training data. And if you run the forward pass properly, I will figure out as PyTorch how to do backpropagation. And I'll give you ADAM and SGD and all of these optimizers. And I'll figure out how to glue the layers together for you. Why are you trying to do this yourself? And obviously PyTorch did not come up with all of these, but it's a very nice example of this. What we're trying to do with DSP is figure out, I don't have layers. I have foundation models. I have a retriever. I have a language model. I have small task-specific models that do summarization or translation or whatever it is. How can we program these the way we program PyTorch, classes? How do we build programs of these things that compose? And what we've sort of developed there is this way of saying, okay, well, at the leaves, where you had layers before, we're going to have something that we call transformations. And these are essentially calls to a foundation model, usually a language model or a retrieval model, but in principle could be other things, where we're not going to tell the model exactly what to do, because that's too, that is too focused on how to do it. We want this to be declarative. And so what we'll say is, hey, your inputs are going to be the following things. Maybe your input is some context and a question and some initial steps or whatever. And I'm going to tell you what the output is. And I'm going to do all of this with data types, but they're semantic data types. I'm going to tell you like, hey, when I tell you that you should generate an answer, here's what I expect in English from an answer. And I'm not going to do this as a prompt that will tie me to like GPT-K, GPT-4, GPT-3, or a specific model. And I'm certainly not going to write this down as like a bunch of examples showing you good behavior and bad behavior. I'm just going to describe the signature. Here are the inputs, here are the outputs as data types, as these high-level data types. And I'm going to have my program as just, this simple, open-ended Python program, plain Python program. You have loops or if statements of these things interacting together. And then what I will benefit, from DSP in the most is now I can go to the DSP runtime and say, hey, here's my plan, here's my structure. I want you to retrieve, these sources, generate several queries, aggregate these results, give them to these models, ask that model to summarize. I'm building up this pipeline, essentially this workflow or this flow chart. And I'm going to tell the model, the DSP runtime, please, map this to a good few-shot pipeline of GPT 3.5 calls or GPT 4 calls or whatever. And, I'm going to like follow that program closely. And, you could add some like annotations there at the code level that say, hey, when you generate queries, they shouldn't be above a specific length, or they should, lead to the answer when we know the answer, or whatever other programmatic conditions. And what DSP would do is it would take this program and 2 or 3, a small number of training examples, as many as you want, but could be a handful, just a handful, and it would simulate your program on them, applying any of the conditions that you have in your code. And what it can do with that is it can discover few-shot prompts that work well in practice. So then it will build these prompts for you in a systematic way that is modular in the data. So let's say in the future, you have new data, like, you're changing the corpus or you're changing the search model that you're using, and it behaves very differently. You don't need to like rewrite your prompts. Your program was always about sort of, the signature level. And that signature never changed, just the implementations of the underlying leaves. You could sort of see how having an abstraction that forces you or encourages you to think at level of high level signatures, and it really discourages prompt engineering and more into the software engineering realm instead, could abstract away a lot of these elements of feedback, because these models can self-improve in that way.
And so what do you view as the future direction then? I mean, right now prompt engineering is a very hot topic. What do you view as the future direction of LLMs, NLP, prompt engineering?
So we are very excited about thinking of these as programming models for working with these, just large language models or foundation models. where you specify high-level plans. You don't just rely on the language model itself making these decisions in like free agents sense. That might be good for some like low-risk applications where anything is fine, but usually, or in many cases, you really do want a little bit more reliability and control. At the same time, we do not want this to end up being a case of specifying all the details by hand. We are optimistic that with the right abstractions, a lot of the low-level details will be delegated to programmatic sort of methods, and I think DSP offers a lot of those. For instance, a lot of there's this growing and I think correct sort of realization that a lot of the future is going to be maybe going to stay essentially, but going to be a lot of smaller task-specific models. But in DSP, I think our hypothesis is more like you might not actually know that they're small task-specific models because they will be compiled by this abstraction that will look at your program and say, I get what you're trying to do, and I've been gathering data for a while, and I can actually just train a small model that does exactly that part of your program better and obviously a lot cheaper than asking a large language model. And in fact, we do have a DSP compiler in the abstraction that you could all this is many of these are things that are, or you can already try out, and whatever isn't there now will be soon. In terms of the future, also I guess one last thing is I think in NLP in particular we've had a lot of, I would say, unhealthy degrees of X is all you need, be it scale is all you need, or attention is all you need, or retrieval is all you need. And, all these sort of proclamations. And I don't think it takes a lot of, rare wisdom to realize that it's probably not true that any one thing is all you need. You got to use all of what you have and, do a good job at a software engineering level and be a little bit more deliberate, get human feedback, scale, sure, that's fine. Use attention, think about HCI with users so that, in mind, so that, mistakes are a lot less problematic. And just in general, think of how to ground these tools. If you want to do math, there's no point teaching the model how to do long multiplications. You could just use a calculator. If you want to search for things, well, just search for them. So artificially restricting ourselves to some X is all you need is probably going to stop being the default position. I'm sure it was going to stay around, but at least I hope it, we go beyond that stage.
I think it goes back to the wise wisdom of everything in moderation.
Exactly. Yeah.
None of the absolutes are here to stay. They'll just keep changing. Well, I wanted to thank you so much, Omar, for joining us on Data Brew and giving us a high level of DSP and the evolution of how it got here. For folks who are interested, highly recommend checking out the DSP paper. There's some very impressive results, including performance improvements of over 120% when compared to GPT 3.5. So super impressive work, Omar. Keep it up. And
GitHub. So the code is public. You could play with the Colab notebooks there.
Awesome. Yeah. I mean, we appreciate everything open source and making this framework effectively available to everyone as opposed to keeping things proprietary behind an API. So really appreciate that.
Thank you.